Okay. Thanks, everyone. Yeah, what I'd like to talk about is what's in the 2.0 preview and what is targeted at the 2.0 release soon. And what I want you to walk away with is basically knowledge of the highlights and also links and references which you can take to learn more about the specifics which apply to whatever you're doing. Just quickly about me, I spend my time working on Apache Spark, mainly MLlib, as a software engineer at Databricks. My background is in machine learning, where I did sparse regression, probabilistic graphical models, and a few other things. And what's really exciting about 2.0 is if you look at the trajectory of MLlib, this is looking at the number of unique commits per release over the years from version 0.8 to 2.0. And as you can see, the number of commits has slowly ramped up, where in MLlib itself, we have some like 850-something commits coming in the next release. And so really want to thank all the community contributions from over 100 unique contributors for ML. Another part of this timeline, which I want to emphasize, is that the DataFrame-based API, of course, you've heard a lot about data frames and data sets for good reason, has been slowly growing over this time period. We introduced it in 1.2 with a Scala and Java API, before they were actually even called data frames. In 1.3, when data frames proper were introduced, we introduced a Python API. 1.5, the very first MLlib API in R. And with 2.0, as you've heard, this is becoming the primary API for ML in Spark. So what does that mean? First, the DataFrame-based API, if you're not familiar with it, is just one using data frames rather than RDDs. And it's also been referred to as the Pipelines API because of utilities for constructing ML pipelines, like was mentioned in the last talk by eBay. So in 2.0, the community has voted for the DataFrame-based API to become the primary one. And this is if you program using MLlib in the spark.ml and pyspark.ml namespaces or packages. And the RDD-based API is not being removed or anything. It's entering maintenance mode, which means we will update it if we find bugs or critical issues. But we're not going to be adding features to it. So apart from this, there were a number of other goals in MLlib for 2.0. And I'm going to highlight a few of these. But for more details, check out the roadmap JIRA for 2.0 at the bottom. So the major initiatives which I want to talk about are, one, generalized linear models, also the Python and R API expansions, and finally, ML persistence, or saving and loading models and pipelines. One other thing I will give a shout out to, which I won't have time to cover, are sketching algorithms. For example, approximate quantiles, approximately counting the number of distinct items in a data set, and so on. You can find out more in this blog post, but I won't have time to talk about it here. Well, so the first two of the major initiatives I'm going to be discussing are for what I'll call exploratory analysis more, or at least they're tools which are really important for the people who often spend their time doing that kind of data science. The second part, persistence, is really for bridging that gap to production, and I think it's been a big step forward for 2.0. So let's first talk about exploratory analysis, GLMs in Python and R. So what are GLMs? Arguably, they're the most important class of models for ML. And I say this because everyone who has done ML has heard of logistic regression, linear regression, seen diagrams like this showing how to classify emails as spam or not. And the idea is that these are some of the workhorses of industry. And you may realize, these models have been in 1.6 and much earlier versions of Spark. But what I mean by GLMs is these are just two elements of a much larger class of models. And we've added a lot more support for other types of models in this class in 2.0. The other aspect of GLMs are model summary statistics. If you're coming from, say, data science and maybe an R user, you'd expect, after you've trained a linear model, to be able to ask, did I actually learn anything useful? Are these coefficient estimates meaningful? And you can now get access to a lot of that information from MLlib. So if you attended the Spark R talk by Shangri yesterday, you've already seen this list. But basically, GLMs in 2.0 support a number of standard model families, number of link functions, and as also fixes for some corner cases. If you've run into little difficulties, say handling invalid labels gracefully, 2.0 will come out and smooth over some of those rough edges. I'll also mention, if you're about to rush out and use these, there are two sorts of APIs to look at in Python, Java, and Scala. So generalized linear regression is the one I'm mainly talking about. It allows you to access all these model families, the summary statistics, but it does have the limitation of supporting about 4,000 features max. And it's because of this solver, IRLS, which it uses, which gives you those summary statistics. If you need to scale to millions of features, you can, of course, turn back to the original or the already existing APIs, linear and logistic regression, which use different solvers, allowing you to do a lot more features. And of course, both of these can use millions or even billions of rows. The other aspect I want to mention for data scientists are the Python and R APIs have significantly expanded. And of course, it's critical because those are extremely popular languages. I won't really have time to discuss each of these, but I want to highlight the big areas we've pushed on. First, in Python, we had pretty good coverage of most classification and regression algorithms, but we added some critical clustering ones, especially Gaussian mixtures and latent Dirichlet allocation for topic modeling. Some meta-algorithms, in particular train validation split for model tuning, similar to cross-validator. Generalized linear regression, some feature transformers, and then model inspection, which I mentioned already. In R, there are currently 4 models offered. Somehow I missed naive Bayes on this list, but there should be 4 items there. Essentially, some very popular algorithms for regression, classification, and clustering. Cool. So these are sort of the items which I think are particularly relevant for data scientists. And what I'd like to do is dive into a little demo to show off some of these. Cool. So let me mirror this screen. Cool. And please yell loudly if you can't read this in the back. But currently, there's not much to read. It's just imports. I'm going to start by creating a cluster. And as usual, this is in Databricks using Community Edition. But the code I'm running, of course, is going to be runnable in whatever Spark deployment you're using. So after this cluster starts up, I'll do some imports. I'm going to be working from Python. And I'm just going to call this, say, the data scientist workflow. Cool. And what I'd like to do is put together a little pipeline, fit it, and in that pipeline will be generalized linear regression, just to show it off. And then I'll show a bit about how you might start inspecting that model. Cool. So let's do those imports. And then after those are done, I want to load data. So my training data is going to be read using the new Spark session in 2.0.read Parquet. And let me type this in. It's going to be a small set of Amazon reviews, some 20,000, and I'm going to cache it. Cool. So that gives me these 20,000 reviews. And let's take a look at that just to see what we have. We'll have a column of ratings from 1 to 5 and a column of review text. You may have seen this in demos before. So I'm going to skip through quickly this part of building a pipeline so I can get to the newer stuff. So our goal is going to be to take that review text, predict the rating, of course. You might phrase it as, say, sentiment analysis. So for featureization, what can we do? Well, we need to get this text into numerical values. And so we're going to use actually some of the same tools you saw in that last talk, taking text, converting it to words. And for that, we'll use MLlib's tokenizer, where the input is going to be this review, just the plain text. And I'll call the output call words. Cool. And so then we're going to take those words and convert it to feature vectors. And as they did, we're going to use hashing TF. this hashing trick to take the input call, which is going to be words, and we'll call the output column feature vectors. And let's say the number of features will be 1,000. And this will let us use the generalized linear regression. Cool. So that's our featureization. For our model, I'd like to use generalized linear regression, where our label column is going to be rating. We want to predict the ratings. And it knows by default to use features column called features. So then we can specify what particular generalized linear model we want. And I'm not going to play around with this too much. I'll just use a very standard one where the family will be Gaussian. I'll specify the link explicitly here as the default, which is identity, just so you see how it's done. And then you might specify other parameters, say a little bit of regularization to try to not overfit. But I'm not going to focus on tuning here. That won't be the focus of this demo. Cool. And so finally, we can take this pipeline and string everything together. Cool. So we have our pipeline defined. And if you've seen pipeline demos before, you know that all you have to do is call fit on that training data set. It'll do the featureization, fit the model, and so on. Tiny problem, so it didn't take long. But now we can say make predictions. And here we'll say model.transform on that training data. It'll return a new data frame of predictions. And we can display it. And that's going to now add a new column of ratings, as well as intermediate stuff like words. Oh, sorry. Can't even see the prediction. Let's select the true rating, the prediction, and the review. Cool. Now this will be more intelligible, and we can actually compare, say, the ratings and predictions. And of course, with more effort, we could tune this and maybe bring those closer together. All right, so if you've seen pipeline demos, you've seen all this so far. But what is new in 2.0 is the ability to then go and inspect the model a little bit further. All right, so our model is a pipeline model, but it has a field called stages, which has each of those stages of our pipeline. And the last one is, generalized linear regression. Cool, so we're going to take our generalized linear model and note that it has this field called summary, which has a lot of different data in it. Everything from, say, coefficient standard errors, which I'm going to use, and number of iterations, if it used an iterative solver, p-values, et cetera. A lot of statistics, which we won't have time to go into now, but which are really useful if, say, you're coming as a data scientist. Cool. So what we might want to do is, say, inspect the model for the coefficients and then ask, are these actually meaningful coefficient estimates, or are they just, noise? So we could, say, take our summary and compare side by side the coefficients with their standard errors and get some sort of sense, if we took more time, of which maybe features have a very obvious signal, which ones, we don't know what we're doing, and so on. Cool. So that's the first part I wanted to demonstrate, generalized linear models and model inspection. And there's a lot more functionality there, so definitely check it out more later on. Cool. All right. So that brings us to the next part, which is MLlib in production. For that, I'll mention two things, persistence, and then at the very end, a slide or two about customizing pipelines, where there's some new nice things there. So why do you need ML persistence? Well, as people realize clearly from the questions from the last talk, there is often this gap in companies between a data science team and software engineering team. Data science will prototype in Python or R, create a model, pass it over to software engineering, who may need to deploy in, say, the JVM. So they re-implement that, deploy it, and so on. Of course, it gets more complex if you have a pipeline with feature extraction, transformation, selection, multiple model fitting, combining results, and so on. And so it can get really difficult to bridge this gap frequently and smoothly. There's extra implementation work just from the extra implementation, different code paths in initial training and in production, and synchronization overhead, slowing down the process. So the idea of ML persistence is to smooth this, where data scientists can create this pipeline, just persist it, calling a simple API like model.save to, say, an S3 bucket, and then software engineering side can load that into Scala or Java in their production Spark deployment and send it off. It'll be running exactly the same code in both of the languages and should return exactly the same results. So what's the status of ML persistence? Well, I'm going to do this in sort of like a 2x2 grid, model pipeline, unfitted, fitted, and I'll explain what each of those are. So a single model, like generalized linear regression, where you fit it on training data, you have coefficients estimated, that's a fitted model. And this was actually supported in the RDD-based API. But what was not were the other three items. So first, unfitted models. They're what I'd call a recipe. You've specified the algorithm, you've specified hyperparameters or options, but you haven't fitted on training data, so there are no coefficients. But you might want to save that in order to, say, rerun on updated data sets later, and so on. I'll call unfitted ones the recipe and fitted ones sort of the result. But in addition to, say, a single model like generalized linear regression, you might have a big pipeline with pre-processing, feature generation, model tuning wrapped around it. And what's now supported is both saving the unfitted version of that, a full workflow, and also the fitted version, where all the models internal to the pipeline have coefficients estimated. Cool. So a little more bit about the details on the status of this and the upcoming 2.0 release. There's near complete coverage in all Spark language APIs. Scala and Java are complete. Python is missing two algorithms, cross-validator and train validation split, but I'll give a link at the end of this talk to a post which is showing how to sort of get around that if you need to. And then R is complete for existing APIs, although again, there are actually some annoyances with saving a model in R and loading it into other languages where it is possible, but we have improvements targeted at 2.1 for smoothing out that process. And again, that link at the end will give more details about that. So all of these have a single underlying implementation of models, of course, as we've followed throughout MLlib. And they use an exchangeable data format, JSON for metadata and Parquet for model data. Finally, I'd like to mention customizing ML pipelines. MLlib 2.0 will include some 29 feature transformers, 21 models for different tasks, model tuning and stuff. But of course, specialized applications require specialized transformers and models. And so you have a few options there. You can extend abstractions. If you're not familiar with these, I'll give the intuition here, but you should check out previous talks about pipelines for more details. Transformers are like feature transformers. Estimators and models are things like generalized linear regression. Evaluators are for, well, evaluating, and in particular for plugging into model tuning. There are a number of existing use cases where people have extended these abstractions and published code online for everything from natural language processing, integrations with Snowball or Stanford NLP, featurization libraries, and others. I'll mention one very popular use case, which is unary transformer, which takes an input column, produces an output column. Things like tokenizer, taking text, producing a sequence of words, normalizer, and so on, are good examples of this. And this API provides basically the DataFrame-based API integrating with pipelines, built-in parameters, getters, and setters, and also distributed row-wise transformation, where all you need to do is specify how to handle a single row. Cool. So I will say this is actually in previous releases of Spark, but what's not is this, which is persistence for customized transformers and algorithms. There are two traits providing persistence, default params writable and readable. And the idea is you simply mix these into your class And you'll suddenly be able to save and load these along with full pipelines in Java and Scala. And this saves and loads algorithm parameters. By the way, this is an implementation detail, which will be great if you're a developer out there. Otherwise, ignore it. Saving and loading algorithm parameters, like param double for, say, regularization, et cetera, it doesn't save member data like a vector val. But you can get around that by storing it as a param vector. For an example, check out this unary transformer example in the examples folder online. Cool, so let me just demo that quickly. We have our workflow. We have our pipeline and model. And so now all I'd like to do is take our model, say write, and I'm going to overwrite in case I need a clobber, whatever is here. And I'm saving this out in that JSON Parquet format, where this is our full pipeline with featureization and the generalized linear model itself. Cool. So then what I could do is say, hand this over to the engineer looking to deploy this and say Scala or Java. And of course here, I'm just going to do it as a very simple demo, but it could be deployed, say, with Spark Streaming or in whatever workflow you have. Here, I'll import pipeline model. And then I'll be able to, say, take this pipeline model class and load that same file, which I just saved from pipeline. Now, what's loading back is, of course, this pipeline model, which includes featureization. And so I can immediately take data of the same format, say, doing spark.read.parquet, Databricks data sets, so on. Cool. And, whoops, I must, OK, cool. Typo in my path. And now I can make predictions. So just as before we did in Python, we can get exactly the same set of computations happening, calling model.transform on that test data. And now we can display it. Let's say predictions.select, we'll select our rating, our prediction, and the review. Cool. And you can see we get exactly the same thing happening in Scala. Cool. So great. Switching back to this, just to recap, we've covered exploratory analysis with generalized linear regression, Python R APIs, as well as production, ML persistence, and customizing pipelines. Again, I'd like to thank the community for the contributions and support, in particular for this work on expanding the APIs and ML persistence. There were a lot of tasks, and yeah, a lot got done. So what's next? The 2.1 roadmap JIRA has already been posted, but it is a constant living roadmap JIRA and could definitely accept feedback from whomever is interested. Some prioritized items right now are critical feature completeness for the DataFrame-based API, multi-class logistic regression, some statistics computations, a couple other models as well. There's also, of course, continuing Python API and R API expansion work, as well as scaling and speed tuning for a couple key algorithms, such as trees and ensembles. I will also mention graph frames. It's not really part of MLlib, but very relevant to a lot of data scientist workflows. If you're not familiar with it, it's essentially graph processing like GraphX, but using data frames instead of RDDs. We'll soon do a release of the package compatible with 2.0, as well as some speed improvements. And if you're interested in that, I'll give a shout out to the next talk in this room right after lunch by Ankur Dave talking about this. So if you're interested in getting started, there's the roadmap JIRA to check out. Download the notebook for this talk at this link. And if you want those details on ML persistence, check out this blog post from Databricks. Cool. So you can check out the preview release of 2.0, of course, and try Databricks Community Edition. And I'd like to thank you a lot for attending.
Awesome. We'll be taking questions for the next 5 minutes or so.
Also mention, I will have office hours today at 2:45 in the expo hall. If you're not sure where that is, ask at the Databricks booth.
Hi. How will MLlib fit together with structured streaming and deployment in production?
Yeah, that's a great question about MLlib fitting together with structured streaming. There is currently not an integration. That said, you could potentially fit a model and integrate that by hand. But of course, what we'd really like to do is provide full integration, both online fitting and online prediction. And that's something which we're beginning to prototype with, but which it'll take time to make sure we get that API right and it fits the workflow which users need for streaming, which I think becomes a bit more complex than batch for sure.
Hi, I come from the software side of things, and one thing that's interesting about this is the notion of the pipeline. It's great for making a model. From the engineering or productionalization side, if I take 24, like 2 or 3 dozen of these models, how do I prevent rerunning all that featurization if I know that I got the same inputs for many of the models?
Right. That's a great question about how do you prevent featurization from going again and again if you have a very large pipeline and say, it depends on how you're using the pipeline. If, say, you're taking your training data, fitting on it, then taking test data, making predictions on it, as data flows through that pipeline, every operation is going to happen just once unless you have node failures and it needs to be recomputed. I think cases where things could be optimized more are if, say, you want to make predictions on that same training data, where, for example, if you fit the pipeline, it'll do the featurization. Called predict on that, or transform on that same training data. It's going to do that featurization again. And the only way right now to prevent that is to basically break your pipeline into parts and do some caching manually. It'd be great to, sort of handle that automatically, but we need to think about the APIs, I guess, for specifying where and when you want to cache in the workflow.
Hi. Is there any plan to support datasets API as well in future?
For datasets? Well, easy answer is same thing. Now, if you look at the API, it'll be a data set of any instead of a data frame, which these algorithms accept. That said, we are keeping in the sort of type agnostic row format because in these workflows, people add columns, they remove them. It's hard to define a type for each. It would be good to know what particular use cases people have other than making, say, predictions with a single model. But within, I think, the full pipeline set, I think that the best use of the integrations is really if you're writing your own implementation of a transformer or estimator, then you could certainly make use of the dataset API in there, where it's a simple operation to convert to a generic data frame to a data set of your specific type.
Awesome. One more question.
Hi, I want to ask a question regarding the models that you train in Spark and maybe use somewhere else. What many companies do is selling predictions as service. That's what we do. Basically, we train the models in Spark, but then we take the models out and then we use them in web services and just use coefficients. So everything that you presented right now is Spark only. The question is, would you have any plans in the future to give the ability to extract it out? So actually we could use this just as a jar or something like that in the web service so that we could run our pipeline in web service to do the predictions.
Right.
Thanks.
Yeah, that's a great question. And it's being brought up more and more as people want to put these in production. It's something like a linear model. It can be quite simple because it's a single vector to specify it. But I think that there are a number of things which need to be done to make it really seamless. First, there are efforts to be able to deploy essentially the same code but subsets of it which are like run in Spark outside of Spark, where there was this initial movement to move the linear algebra library like outside of Spark so that it could be used in, without a Spark context existing. And that's the beginning of what's needed to really have local versions of those models. Yeah, in the meantime, I think that the best options tend to be, if you have a simple model, of course that's simple. If you have some featureization, I think one critical thing we did do in the current 2.0 branch is switched using murmur #3 everywhere, which is like standard library, where you can like get exactly the same featureization results outside of Spark. But yeah, we need to offer.
And what do you think? What would be the time frame for having that? A year, 2 years, or guesstimate? Not a
Right, good question. I mean, I would say definitely within a year, but I'm not sure of an exact date. I hope sooner. But.
Awesome. That's all the time we have for questions, but thank you all for coming.